Hey everyone, my name's Yifan. I'm a grad student at UC Berkeley studying computer science in the database group. So my talk today is called Knowing What You See. Let's talk about front-end consistency. So as you may have noticed, it's a little bit inconsistent, no pun intended, with the abstract, but it's still in a similar domain. And another point that differs is that I am no longer a first-year grad student, proudly entered my second year. So this work is some research that my group has been focusing on. So anything that I say that's useful, that's definitely shared results, and anything that's wrong, I take complete credit. So before I get started, and since we're a pretty small crowd, I just want to get a sense of how many of you identify as a front-end engineer. Great. And back-end engineers? Cool, wow. So how many of you have heard of ACID transactions? Hold your hand up if you know what multi-version concurrency control is. Wow, okay, all right. This is a tougher crowd than I expected. I thought I could just say things. Cool, so I guess as you have sort of probably guessed from my questions, this talk will straddle both sides of the different fields. And hopefully by the end of the talk, you will gain appreciation for the other side. Because as I suspect, you probably don't know too much about, if you're a back-end, about front-end, and front-end about as much about back-end on average. So what do I actually mean by front-end consistency? Intuitively, it's basically the same as the dictionary definition. So conformity in the application of something, typically that which is necessary for the sake of logic, accuracy, and fairness. So for our case, with visualization, we actually care more about logic and accuracy. And let's take a look at some examples to sort of get an intuitive sense of what I mean. Usually it's fine. When I open my Facebook, I don't really expect in particular to see my ads show up with the news feed. And when I open my Twitter, it's okay that I don't see the media before I see my friend's tweet. I can get a still vague sense of what's going on. But sometimes you do have expectations, and you don't see what you expect. So how could this happen? Imagine that you're driving through the middle of seemingly nowhere, and you're desperately trying to find a dinner place. And this thing shows up for a good half minute. It could be a pretty frustrating experience, and let's take a look at what actually happened step by step that caused this to show up. So here's a pretty simple time diagram with the user, the front end, and the back end. So the user opens the application, the front end makes a request to get the map and get the pins. However, the map is a little bit larger in terms of data size and takes longer to load. So the pin comes back first, the app renders it, the user sees this view, and then for the time afterwards until the maps arrive, it's just going to be like this, which could potentially be a little bit problematic. And we call this, the yellow range, slightly inconsistent. So many of the front-end engineers sitting in the room may already have a lot of solutions. Like this is such, like, why don't we just block it, etc. So please bear with me. We're just getting started on the appetizer here. I'm sure the problem will get a little bit more interesting as we go. But before we even go there, let me just enumerate through how common this problem is. And oh, by the way, we're going to name this anomaly reordering, because as we see, the map arrived out of order per the request order. So another simple example. Just a few days ago, I was trying to print some posters on Walgreens, and I was expecting my picture to show up, drag it over, and then print it and be done with it, but I didn't see anything. So that was really confusing because I didn't know whether I should wait or refresh. So I'm sure many of you could identify having used terribly designed applications like this, and this anomaly we call varying delays because there was no signal for what was going on. So the anomalies we've seen so far is rendering and varying delays. So as the front-end engineer sitting in the room, we can just simply block and show both of the data results as they come back. And for the varying delays, add a spinner, right? Problem solved. However, the real-world scenarios actually get a little bit more complicated. So let's take a look at this visualization dashboard. So there are this map region, which corresponds to the different visualizations we see on the bottom, and the user could choose to zoom in. So here we zoom into the African region, and we expect some visualizations to update. So how many of you have noticed that there were updates or there haven't been updates? It was pretty subtle, right? Again, the UI front-end engineers would say, oh, this is just terribly designed. There's no feedback. That is definitely true. But this is basically just pointing out how, as a user, you might be unclear what what the data corresponds to. And so in this specific example, share by region loaded first, customer distribution loaded second, and sales actually never refreshed. So the time diagram, as seen before, is sort of the user zooms in, the front end issues multiple requests, and then they arrive with some different delays. And so in this yellow region, some things are out of sync. And if there's no sort of feedback mechanism, it would mean that the user's looking at the wrong data and drawing the wrong conclusions. We call this anomaly mistaken correspondences. So far I've been naming the anomalies so I can refer back to them once we actually have a good way to sort of deal with them all. Again, some of you may say, oh, like this complicated example you show is actually really simple because we can just prefetch everything. And my pushback to that is sometimes it's not all possible, right? Imagine the user just selecting some arbitrary regions because they have very complex analysis needs. With the cases like this, it's very hard to pre-compute all the data and just squeeze it all to the front end. So that's probably not going to be the perfect solution. Some of you might ask, why couldn't we just split into grids? And then that way we have a finite number of requests that's pretty much manageable. But this limits the flexibility of how the user could interact with the UI. So in this case, the user can only select multiples of the grid. So here we see a very canonical example of trade-offs that we deal with every day, like functionality versus performance. Some of you might also ask, why couldn't we just ask the backend engineers to make things run faster? That's always the perfect solution, right? It's none of our front-end engineers' business to deal with any of this crap. So the reason's actually pretty tough, as many of you have laughed, so I imagine this conversation may have happened sometime in the past. So the first issue is that the server compute time might just take a while, because if you're doing aggregation over 1 terabyte of data, which is no longer like a big number for us entering this big data era, it's really hard to fix. And then there could potentially be cache misses because the data is not really popular, analyzed among different people. And we've seen that this is a very tough engineering challenge. There are a bazillion of new databases that's created every day just to tackle like application-specific needs, for instance, Amazon Dynamo as an example. And that requires a lot of engineering power. So this is not something we can just trivially say to a single backend engineer, here, solve my problem in a day. And there's actually more subtle issues where it's completely out of your control because the application has the user has a slow internet connection. And in that case, it doesn't really matter how fast your servers compute, the bottleneck's at the client. So you will still have to deal with these inconsistency issues. And worse still, there are actually more anomalies that are a little bit more problematic than just server-end delays. So let's take a look at this real-time interaction. And I'm sure many of you are aware real-time is starting to replace big data as this new hot thing everyone's chasing. And it's only a matter of time before we start extensively using visualizations that are real-time. So actually this morning I was looking at my Uber app and tracking my driver because the rain was pouring and I couldn't make the short 10-minute walkover. So and it was late, and I was so confused because I kept on looking across the street, and there was a driver waving at me right in front of me, and I was like, this can't be the driver, this can't be the driver, because Uber told me it's still 3 minutes away. So that's another example where the real-time aspect of the visualization is actually really important and comes to our day-to-day lives. But anyhow, let's take a look at this example where imagine you're a stock trader, and this is some ticks that's being updated over time. And you're interested in the region between 60 and 25, and you select this. And you see some average dividend that's calculated based on this tick. And immediately afterwards, there were some real-time data being updated. And it becomes slightly unclear what this new dividend is being computed as. Does it actually include the yellow region, or did it stick with the green one that we selected before? So this is an anomaly of unclear selection that's caused by real-time interactions. Another example, which is a little bit more subtle, is that imagine as you're doing the selection, the data started updating. And your selection actually finished after the data updated. As we know that as humans, we don't really have like 1 millisecond response times as we expect all our servers to have. So in this case, it becomes a little bit problematic whether you actually selected 25 to 55 or this new region that's like 40 to 60. So as you can see, this consistency problem gets pretty hairy as we start giving more and more richer functionalities. So in this case, it's actually a wrong selection. And one last example before we move on. So here we have an incremental visualization where you slowly select the bar charts, and the visualization is supposed to update as it goes. So the orange bar's correspondence came back first, and then the second one for the blue came back. So some of you may have noticed that some issue happened right here where there was an overlap. So if the user were just to look at the final state of the visualization, they may not realize, oh, there was actually orange dot below it. So this anomaly we call overwritten marks. But some of you sitting down there might be like, well, wait a second. So I think asynchrony could be my problem, but this is totally just a layout issue, right? Like, how is this even related to consistency? So again, like I'm mentioning this to sort of include the breadth of consistency problems can cover, and you can definitely try to brush this aside as a layout issue and solving another way. But as we probably all experience, most engineering problems aren't clear-cut bucketed. And I would say that this is definitely a layout issue if it's a single selection and you're updating everything all at once. But because here there's a delay and you're not seeing all of the data all at once, so this could be treated as a consistency issue because it's actually like data changing over time. So we've sort of found all of the consistency bugs that could possibly exist, and there's probably more. So we've seen reordering, varying delays, and concurrent updates. So this is a good point to sort of step back and say, what do you actually mean by consistency? We're engineers here. Stop giving me these like fluffy words. The bad news, however, is that consistency is in the eyes of the beholder. And this is not just because we're dealing with fluffy UI. For those backend engineers, you probably know that consistency, the word, is not really well defined, even in ACID transactions. The joke goes, and I do not claim this to be completely true, that the C was created so that the acronym sounds cool. The reason is that consistency is dependent on application semantics. Let's take a look at an example in vanilla systems. So you have a database, and it's for financial services, and your checking account must have balance greater than 0, right? If it's below 0, it's inconsistent. And if you have a credit card, you only require the balance to be greater than a certain negative amount. So in that case, if it's slightly negative, it's still consistent. So this is an example of when consistency is dependent on application semantics. I see some of you are not quite agreeing. I would add the caveat that the consistency in CAP theorem is well defined, and it's a little bit different from what we're talking about. And I'm not going to go into the details. I only mention CAP theorem so that you guys know what I'm talking about. So now that we've sort of understood some of the consistency issues we see in the front end, some of you probably are still unconvinced. Like, why am I sitting here? Who cares? So I would argue that the first group of people who care are the data analysts. So again, as we've seen, this consistency issue is very relevant for data visualization, especially interactive data visualization over big data. So the analyst would be frustrated if she doesn't know what state the UI could be in at any point in time. So imagine your text editor just randomly giving you characters as you're typing. That must be frustrating, right? I would imagine that's what translates to for the visual analysis case. And then the data analysts might propagate the problem up to the front-end engineer and say, hey, why don't you fix this issue? I'm really confused. The front-end engineer may design a ton of callbacks and fall into what we would normally recognize as callback hell, or they can say, oh, back-end engineers, go fix this problem for me. If everything's fast, I don't have this problem. And we've discussed the limits with that solution before. And the worst case, actually, is when the user doesn't realize there was inconsistency. So they might draw the wrong conclusions. This is pretty terrible. And so today we might not be living in the Iron Man world yet, but as we've seen, big data is starting to sort of flow into all aspects of our lives. The future is now, basically. And we see a ton of startups integrating very fancy real-time dashboards that are very complex looking all over the place. Tons of startups. So these startups are part of our mission-critical tasks, day-to-day, tasks that are responsible for your health, your money, and your policies. So hopefully I've convinced you by now that this is actually a worthy problem that we should all take a look at. And there are many very good front-end engineering out there, and there are a lot of existing approaches to tackle this problem to some extent. So let's take a look at some existing approaches. The first one is blocking. So after the user zooms in, instead of updating things asynchronously, let's just get rid of all the visualization because they're inconsistent, right? So let's wait until all of the data has loaded and then update all at the same time. This is OK, right? It helps us with increasing consistency, but the interactivity is pretty meh. And the ease of understanding is decent because you know where you're getting, right? When it's not loading, you know it's still processing. And the ease of programming is OK. Like, it's not as complicated as adding all these widgets, but you still need to have quite a few callbacks, et cetera, to synchronize your data results. Another example, another solution is using spinners. So after we perform the zoom, the sales and customer distribution starts to sort of load, and then when the customer distribution arrives, the spinner stops. Great, we know exactly what's going on, and we know that we shouldn't trust the sales visualization, so we wouldn't make the wrong conclusions. However, I would make the argument that spinners are sometimes not enough. So when we have multiple zoom levels, for instance, here, once we zoom further in, they're all spinning. So we basically get this binary notion of, is it up to date or is it not up to date? But we don't really know how many steps forward it is. And this could potentially be a problem if you have a very busy analyst who's just like selecting things all the time. And if your server is really slow, then 90% of the time when you're interacting with the visualization, everything will be spinning. So that would be a pretty bad user experience. So this, we argue, is OK for consistency because, as we've mentioned before, it doesn't cover all the cases. The interactivity is OK because we can see some partial results. The ease of understanding is, once again, just OK because you could have your visualizations be in different states, but have the spinner running all the same way. And this is probably not that easy to program because now you have this like gazillion widgets to keep track of, and they could sort of work with each other in a combinatorial way that you have to track many different types of states. Another solution is to use labeling. So I did define sort of consistency as knowing what the logic is or what the current state of the UI is. So why don't we just label all of the visualizations we see? So here your starting lat is -85, your ending long is like 180, et cetera. And when you zoom, let's just update all of these different annotations. So this is OK because it is perfectly consistent. If you stare at it, it gives you all the information you need. And the interactivity is pretty decent because you can get data as they arrive. However, the issue is that this is not very easy to understand. We're essentially defeating the whole purpose of visualization by adding on queries to annotate these data, when in reality, we should be using visual cues and correspondences to actually show what the data means. So this is an example of when it's not that easy to understand. And it's probably not very easy to program in a way that's similar to the spinners, but perhaps even more challenging because you have to now deal with a lot more layout issues and annotations, et cetera. And at this point, we still haven't accounted for the anomalies we've seen with the unclear selection and overwritten marks. So it's not perfect in terms of solving our problems. Let's just take a quick review of the design space before we start looking into some potential options. So in the anything goes approach, consistency is bad, interactive is great, ease of understanding is bad because we don't know what's going on. Ease of programming is great because that's essentially what you get with JavaScript callback, just writing vanilla JavaScript. And then these are the 3 cases that we already discussed. So at this point, I've probably lost the interest of most of you backend engineers. It's like, this is none of my problem, just a lot of like front-end designs. Why do I care? I don't even need to make things run fast, as you have explained to the people, right? But if we stare hard enough at this problem, it really begs the question, is this front-end engineering or is it distributed systems? Because now the front end has to deal with all these issues of requests, delays, asynchrony, concurrency, and consistency. Like, these are all the words that you hear in like distributed systems 101 or database 101 classes. I think at the core of this problem is that it's all just data-centric programming. Because most of engineering, some of you might disagree, is just piping data around. So it's not surprising that the front end starts to look similar to the back end once we get into these more complex visualizations. So my punchline is that the front end is a database. And with this perspective, we can solve a lot of the issues we've seen previously. The reason is that database techniques have been dealing with reorderings for a very long time. And they can deal with reordering to bring consistency and do this declaratively. So let's take a look at how exactly it could help us. But before I do that, I want to sort of show this is not some crazy talk based on someone who's extremely biased, who does research and thinks about database all day long, and is actually agreed upon by a lot of the very hip front-end libraries. So the first one is D3. D3 manipulates the documents in a way that's very similar to SQL's select project join pattern. Because of time limits, I won't go into the details of why exactly it is, but if you think about the select all, P, and then the exit and enter, that's very similar to joins. And reactive X, rx.js, or React, etc., you probably have all heard, deals very much with the streams and iterators, which are very intrinsic to database implementations ever since the 70s. So again, this is sort of a programming paradigm we're very familiar with in distributed systems. And lastly, there's the very recent Facebook relay, which operates in a manner that's very similar to query optimization, where the data fetching actually decides the where and the when and the how to fetch the data. That's essentially what traditionally data query optimization would do. So hopefully by now I've convinced you that there is some merit and in looking at the front end as a database, and I'm not sort of going crazy here in making that claim. So let's step back a little and think about how to use this newfound perspective to help us deal with inconsistency. So for the remaining time I have, which is not too long, we're going to take a look at the detection of inconsistencies and try to propose a somewhat formal framework so that we can capture all these issues in a more systematic manner as opposed to looking and saying, ew, this doesn't make sense to me. Pretty low baseline. The next is once we detect these issues, how do we prevent it from happening at the first place? There are 2 main approaches. One is that we just ensure consistency and never have the user see anything that's inconsistent. Or we can communicate the inconsistency and tell the user, look, this data is not correct yet, just wait. Sounds familiar to the systems people? This is very similar to eventual consistency. So anyhow, this is currently going through pretty active development, and there could be some good ideas and bad ideas. And if I ever say anything that you disagree with, I'm more than happy to hear your ideas and criticisms. And please talk to me afterwards or chat me on Twitter. So let's get started with the detection formal framework. So I did mention that the front end should be treated as a database, and as we know, databases come from a relational model. And let's take a look at exactly how this should be interpreted as a query. So as the user is selecting in view 1, we have the stream of mouse events where the user mouse down, we have the XY position, and then there's a mouse move, and then further mouse up. So streams could be also queried in some extension of SQL. This has been actively researched in the 90s. It's called SQL. So there are a lot of existing approaches to deal with streams. And in some sense, streams are just a table in time. So it's not a very far stretch to say that we can incorporate streams into the relational model. And then this information is joined with the marks that are underlying this visualization. So here we know that the view 1 has rectangles of x, y's underneath the hood. Essentially, this is doing hit testing. So we get the results from the join of these two tables and join that with the base data, which is essentially simulating this backend server request, where you say, go fetch me this data that's related to these data points. And then you get the result. That's the result of your query, and you render this to the front end. Now that we sort of see how the interactions could be modeled as a query over different tables, let's model the interaction a little bit further as a transaction. As most of you probably know, a transaction is defined loosely as this notion of executing a set of commands atomically without interference by other transactions. So, and it's usually identified by its reads and writes to the database underneath the hood. So our interpretation of the interaction is that it's a read of the underlying tables, and it's a write of the UI when it starts to render the data. So there's this parallel of reading the UI's tables and writing to the UI's tables. And this is pretty important to set up our problem, because without this notion of a read and write, we can't really establish a very concrete notion of conflict. So a data flow way of looking at this relational/transactional system is that the user issues the interaction, which performs a read, which sends a request to the server, like to perform the query, the join, which gets the result back, and it's a write to the UI, which further renders the data to the user. And somewhere along the way, hopefully, there's some confirmation of the interaction. So for instance, when you brush, you can see your brush, and that's rendered immediately, which is also considered to be a write. So that was a little bit too abstract. You're probably missing all the fun animations and visualizations we were seeing a lot of earlier. So let's take a look at a concrete example of conflict. So again, the same example as that we had before, as the user is clicking now on the green part, on this blue part, I couldn't read, and you would have this register of current interactions, which registers that the orange is still active. And when you click on the blue, it attempts to update something that is written by the current active interaction, i.e. transaction. And because there's a lock on it, it's detected as a conflict. If you decide to overwrite this conflict, you would essentially end up overwriting your previous mark. So this is an example where we were able to use this model to detect conflict on the pixel level to find one of the anomalies we mentioned before. This is essentially a write-write conflict for those of you who are familiar with database distributed systems terms, where there are two interactions attempting to write to the same pixels during their execution. There are, of course, other types of conflict as inspired from sort of this conflict reasoning framework, which is a read-write. And let's take a look at how this maps to our previously seen streaming example. So here, when the user does a selection, as we mentioned before, that's a read on the existing table. However, as the user was performing this read and executing the results, the query with the backend, there was actually a write on something that it was reading from. So this is a read-write conflict. Again, we've demonstrated how this model has detected one of the anomalies we've seen before. The curious case when the human is involved in the loop is that there's a write-read conflict due to the human latency. So let's take a close look at this example where as the user was interacting, the data has been updated. So this is essentially when there was a write, there was a write immediately before the read. And this usually you don't see in systems as much, but is like intrinsic part of what happens when you bring a human into the loop, is that we don't have a response, like reaction time on the order of milliseconds. So when we decide to do something and things update during the period that we're performing this read, it's actually a conflict as well. So hopefully by now I've convinced you that using this framework, we can fit all these different anomalies we've seen before into this detection framework. And with 10 minutes left, let me quickly move on to how do we actually solve this problem. So the first is to ensure consistency. A technique that we've seen is blocking, which I argue is very similar to what backend folks do for locking. And it's essentially locking on the entire UI. It's saying once you've done this interaction, no other interactions or transactions can actually update the same UI, so you're just blocked there to wait. So if we extend this analogy to inspiration from systems algorithms to more front-end techniques, we can imagine to have more granular locks. That way, you don't prevent interactions that doesn't actually interfere with each other to happen simultaneously. The question is, can we draw more insights from algorithms from systems concurrency? And the answer is, of course, yes. The first one is interaction constraints, which draws inspiration from database constraints. Let's take a look at the anomaly we've seen before. So here we can make the statement that the pins would only render if the maps have rendered. So you show the maps first before you show the pin. It's a very declarative way of describing what you want to achieve. Another thing that's inspired from systems, like the CRDT or lattices line of thinking, is that you can merge the updates so you can avoid these conflicts. So here, once we see that the blue is attempting to update the orange, instead of rejecting the blue's update, which is a little bit too aggressive, we can say, let's make both of them transparent. And that way, you can avoid the conflict by addressing the issue here. Again, this is not a new technique. The front-end folks probably use this day to day. But the point is to show how there's this very close tie between systems thinking and front-end designs. Another example is actually inspired from multi-version concurrency control. And the basic idea, I won't go into details of explaining what this exactly does. And this is a very loose coupling. It's an inspiration. So what it maps to for visualizations is that we can create snapshots to avoid conflicts. So again, in the streaming example that we've seen many times of, once the user has performed the selection and the streaming data is attempting to update, instead of updating in place, we can just create a new snapshot and update it in a different place. That way, we avoid the conflict altogether by writing to a different version. A more exotic / involved application of this visualization snapshot is to apply it to a cross filter. So here we have the user selected the time of the day, and it's currently being processed. This very busy analyst wants to take another look at what would happen if the filter is additionally based on distance. That would essentially, so the system anticipates a right-right conflicts and splits it into different view. And similarly, if we add additional filter for arrival delay, that creates a new snapshot because you could potentially create conflict. The good thing with this design is that all of the different snapshots could be executed in parallel, and the user is not prevented from performing any interactions. So this maps back to sort of how multi-version concurrency control guarantees that we don't have to block any of the reads. And this also enables time travel, which some UI design for visualization have argued to be a pretty good design. And lastly, let's move on to the other part of prevention, which is communicating the inconsistency. We've already seen this before, so with blocking or adding labels, these are all ways of communicating the inconsistency, and they're pretty good. And the only thing that we can improve on this is sort of making it easier to program. And the sort of pitch from the system's perspective to avoid callback hells is that we can have some sense of the global state so as to not design too many callbacks and to check for different states. This doesn't do it enough justice. If you're interested, please refer to some of the work I will link into later. So the idea is to deal with inconsistency declaratively with this sort of more system perspectives. And one project that we're currently working on is to develop an API for the front-end state wrapping that into a shim layer for consistency, where the user could just provide us with interactions and request handlers, and we detect the conflict. The user could choose to sort of just acknowledge that there are a lot of conflicts and know how well their application is doing in terms of like slow proofing or consistency proofing. And to take that step a bit further, they can use this information to prevent conflict or communicate conflict. Again, this project is currently undergoing heavy construction, but will hopefully be ready in a few months' time. As computing and data becomes more ubiquitous, the distinction between front-end and back-end, data and non-data, is dissolving. I hope I was able to convince you that consistency is starting to become a real problem for interactive data visualizations and some other front-end problems. There is some merit in taking a more data-centric lens to look at front-end programming. If you're interested in this philosophy or outlook, there are a lot of related work that's available to follow up on, and these slides will be made online somehow. So with that, thank you so much for being here. I'm looking forward to your feedback. Please talk to me afterwards. Thanks.